Uh, Hi. I'm Krishna. I'm the second author of this paper. Unfortunately, my student couldn't be here. Obviously, he did most of the work. So today I'll talk about a DSL extension to Java, which allows you to make your APIs defensive by design, right? I don't have to spend too much time here justifying why APIs are important, but I have some slides, so I'll just go through them. Uh, uh, APIs are like they allow you to reuse popular functionalities, right? And they improve software productivity. One thing that is not understood is how prevalent they are, right? In a recent study of 1.5 million Java files, there were about 34 million calls to APIs, which kind of paints a picture on how prevalent they are. And um, I don't need to go further than point to today's keynote, which also talked about why libraries are more interesting to programmers than actual new languages, right? So the setting is that APIs are quite important. Um, even though they are prevalent, misusing them is quite common and in some cases extremely costly, right? So Zoom settled recently about $85 million because of security flaw. Of course, there were other reasons that contributed to this flaw, but one of the things was that their encryption, their calls to the encryption API that they were using was using a parameter to specify the algorithm, which was quite outdated, right? So the security flaws were there. And this was one of the things that also contributed to it. So the point here is that API misuses can be costly, right? Um, and this here, this slide, it kind of paints a picture on why that is the case, right? Because the implicit usage rules of what is correct API use is not kind of straightforward, right? Here I have a couple of examples. One on the top is both of them are from JCA, right? The Java's cryptographic library. Here, the idea is to, when you create an instance of a cipher object which is needed for any kind of cryptographic task, you would need to specify the algorithm, right? So here, the algorithm chosen is AES, right? But what is not explicit here is that you're expected to also specify a blocking mode, right? If you don't, it defaults to ECB, which is considered, you don't have to know what these words are, but the point is that ECB used to be secure when JCA was invented, but it's no longer secure, right? So here you can see why it's obvious to miss these kind of details and misuse the API, right? Below is another kind of API misuse, which is also quite common. I think it's the most common kind of misuse, where there are implicit rules on what kind of order your methods must be called, right? Here, for example, when you are you creating a signature object to sign your data, you need to uh, you need to first instantiate it, then initialize it, call init sign with whatever key you want, right? And then you would need to update it with the data one or more times, as represented here in the state machine, before you actually call the sign function, right? And this is also something that is that happens quite a lot in practice, that people don't call the methods in the right order. They miss out important methods, right? A popular example, an obvious example I can give is, like, if you open a file, you're supposed to close it, and you would be surprised how many people forget to, right? So this is one of the reasons why API misuses happen a lot, because these usage rules are implicit and they are not straightforward, right? One can argue that why not just simply refer to the documentation, right? I don't know what's happening here, but documentations generally don't exist for all libraries other than like really popular ones. And even if they exist, past studies have shown that they are not adopted in practice quite well. And this is just my theory, right? On why they are not adopted in practice. If you look at the documentation for JCA, it's like 64 A4 size pages. So go figure, right? So obviously documentation is not the path to avoiding API misuses. The other path is obviously static analyzers. You can specialize static analyzers, hard code them with what is wrong? Hard code them with API misuses, kind of like saying, okay, if you have these patterns, then you've violated the API's constraints, right? Uh, But the problem here is that API usage rules evolve, right? So as you've already seen, what is correct use, especially in the security area, what is correct use of an API may no longer be correct few years down the line, because new hacks come in the picture. And this is not just for security algorithms, this is for all kind of APIs, right? APIs version, which means what is correct use also evolves, right? So the point here is that static analyzers, if you do have static analyzers that are specialized for API misuse detection, you would have to constantly keep updating these rules, right? Another approach is what was adopted by this. But what in this paper we argue that this is the state of the art, or before us, this was the state of the art in API usage specification language. The idea here is that your static analyzer is not hard-coded with these usage patterns, but rather they rely on rules written by API designers, right? So you don't have to understand all of it here, but if you here on the left hand side is a counter function which has constructors to initialize them. You can increment, decrement by values, and then you can freeze them, right? The rule here, the order rule here, essentially is a regular expression that says that you need to call init, which is one of these guys, right? One of the two constructors, and any number of calls to change, which would be either increment, decrement, or take, and then you would have to finally close it with that, right? So this is the path that CrySL has taken to essentially allow the API designer to specify the order in which the methods must be called. And of course, there is also constraints, which are essentially contracts on the values of these parameters, right? So there are other things, but you can refer to the paper if you want more details on how CrySL works. But this is not a contribution of this paper. I would even recommend that you go and read CrySL, right? This was a good, this is a good step in the right direction, but this still requires a tool to be installed, which means there needs to be a static analyzer that consumes these API specifications and then checks for compliance with your code, right? And developers don't like to keep installing tools, right? They've barely adopted the basic bug detectors and sometimes whatever their organization imposes on them. So it would be a push to actually ask them to use these API misuse detectors, right? So that's where the motivation for jGuard comes in. So jGuard essentially takes from the leaf of CrySL. So jGuard is essentially allowing you to specify or allowing API designers to say what are the correct ways to use their APIs. But where it differs is that these kind of rules are encoded into your API implementation itself, right? So we have an IDE where you can import your, so currently the implementation is Java, but I think the concepts can be extended to other languages. So the idea here is that you would import your API into this jGuard IDE, and then you can annotate it with these specifications, right? So I'll go through what kind of specifications can be there. And the interesting thing here is that once you've done it, there is a compiler which translates jGuard's code, jGuard annotated code, into regular Java, which means that as the end user, you don't need to make any changes other than replacing your existing jar of the API with the checks enabled jar, right? So these checks would be kind of compiled as exceptions. I'll give you some examples in the next slides, right? But yeah, so the idea is that you're making libraries kind of defensive by design, right? And the end user doesn't need any tools to get access to the misuse checks. So what kind of features does jGuard support? What we did was we motivated our features from two. So first we needed to understand what kind of misuses happen in practice. So we picked two papers which we thought was kind of the state of the art in there is no explicit paper on, we couldn't find an explicit paper on API misuse categorization, but there were two papers. One was a survey, the one on top here is a survey on API misuse detectors over a span of 10 years. And then below is just a benchmark for API misuse detectors, meaning it's just a benchmark of actual misuses. And both of these papers, we looked at these papers and we curated the kind of misuse categories that happen in broad. Again, I'm not going to go through all of them here, but the idea is that, and we motivated the features of jGuard based on this, right? So the first thing is behavioral specifications are essentially contracts on your method parameters, and you can express them in using what we call requirements in jGuard. I'll show them in the next slide. And then method call sequences can be expressed using concepts, expressed using a combination of guards and what we call guards and consequences, right? So guards are the fundamental unit of expressivity in jGuard, right? So I'll show you what I mean by them with this very simple example. So I told you that guards are like, so first thing is you need to tell the jGuard compiler, you need to first tell the jGuard compiler what classes need to be compiled in this special fashion, right? So, and you do that by saying that this class is verified, right? You just add this annotation verified, and then you can declare guards. Guards are essentially kind of gatekeepers that that keep track of the state of the object itself. You use guards to keep track of the state of the object. I'll just go through this encryption started guard here, right? And then you can, as I told you before, you can have requirements and consequences. Here, the requirement for this init method is that, well, it should not have, the encryption should not have started before, because init is what is going to start the encryption, right? So here is the consequence, which is when it returns. So there are different kinds of consequences we support. So essentially consequences are reactions to events that happen after the method is executed. So you can think of requirements as checks that happen before the method is executed, and consequences as checks that are checks that happen, or not checks, but rather events that happen after the method is executed, right? So requirements, here in requires, you can actually put in any Java expression, right? And you can have access to these guards, right? This example is obviously too simple to understand how expressive jGuard is. And when you're returning, so essentially what it says here is that when it returns successfully, right, without any exceptions, then please set the encryption started to true, right? So this is a simple example that shows in a nutshell how you can use jGuard, right? I told you that jGuard compiles jGuard code into regular code, right? I'll briefly go through how requirements and consequences are compiled. So requirements are fairly simple, right? As I told you before, requirements are checks that happen before the method is executed. So at the top of the body of the method, it would simply insert if statements for each of these constraints that are there in the requirements, and then it would report the appropriate misuse, right? So since we have an ID that is built on top of MPS, you can actually specify how the reporting looks like also. So you can check out the artifact. Consequences are a little bit more elaborate in the sense that here, for example, this method has two consequences. One is if it returns true, set G1. And if it throws this exception T1, then reset G2, right? So since consequences are reactions to method after its execution, the idea here is that first jGuard would convert the current method into a wrapper for so there would be a wrapper for the old body, and then essentially the return value is stored in a variable, and then you would have checks which essentially check for each of these consequences and set your guard or reset them accordingly, right? So requirement supports all kinds of Java expressions, but consequences currently support only setting or resetting guards as reactions to events, right? We also have other features, but I'm not going to go into the details in this talk. We support what is called meta variables. Here, the idea is that API specifications, one, they evolve, but what they also have is variability in terms of what the context is, right? To understand this, what is secure? Secure usage, how you securely encrypt using JCA is differently defined for whether your client is using BSI, which is a German standard, or NIST, which is the American standard, right? So this is just an example. You can have other sources of variability that are that come in with the API usage specifications, right? So what is happening? The idea behind meta variables is you can maintain families of usage specifications in a kind of compact fashion. You don't have to keep on writing these specifications again and again, right? I recommend you to check out the paper to understand how you can write these meta variables. And external state variables are something that came to us while we were implementing jGuard, because we realized that jGuard essentially injects code, right? And you can't inject code into core libraries like JDK, right? So we introduced this feature called external state variables, which allows you to kind of have these external static classes, which again, I'm not going to go into the detail, but we are hoping that external state variables won't be needed in a real life scenario, because the idea behind jGuard is that someone who's implementing an API would use jGuard, and that's not going to be the case with JDK because it's already done, right? So the key results. So first thing was we took MoveBench, which I talked about before, which is like the state of the art in API misuse benchmark. We tried to express the top 10 prevalent misuses there, and then we were able to cover up to 90% of them. Where we couldn't cover were scenarios where actually you can't reason about dynamically. To give an example, one of the misuses about detecting whether a password is from a hard-coded string or not, and there is no way you can reason about it in a dynamic fashion, right? So this is where, so we kind of have a fairly good understanding of where jGuard fails. So it's not like, it's not like just random 90%, right? Again, here is an example of the top or the most prevalent misuse, which is essentially from the class byte output stream. The idea here is that before you flush, you shouldn't have any more pending writes in your stream before you kind of use your byte array, right? So for that, we have this guard called has pending writes. You don't have, we don't have to go through all of the details, but this is just to show you how, till now I showed you kind of synthetic examples. This is to show you how a jGuard annotated code would look like in practice, right? So the other contribution of the paper was also, I told you before that in the paper we argue that CrySL is the state of the art in API usage specification in terms of the kind of misuse categories it supports. We made a formal comparison between CrySL and jGuard can express all of CrySL specifications, barring these static analysis things like detecting hard-coded passwords and things like this. But jGuard can also do more, right? Because CrySL can only support these regular expressions. jGuard, in a sense, can support the requirements can support any kind of Boolean expression, right? Oh, sorry, the constraints are so the constraints in CrySL are kind of like restricted to certain operators. jGuard isn't, right? And guards are more versatile than regular expressions supported by CrySL. Where this comes in handy is a prevalent misuse in the iterator class, where the usage pattern says that it's obvious if you before you call next, you need to make sure has next returns true. This is a very simple thing, but we were surprised that this was one of the most prevalent misuses. And this is not the kind of thing you can do with a static analyzer anyway, because you need to reason about the return value of a function, right? Well, this is some things that things that come out of the tooling from jGuard. Essentially, jGuard can support reusable constraints, and we had to do this a lot, right? So essentially, the idea here is that you would have this wrapper method with only these requirements, and then they are like kind of used in multiple places, the verify engine parameters, right? We observed that this is kind of tricky with CrySL anyway. We also compared actually it's not expressiveness, I'm sorry. We compared the accuracy of jGuard's misuse detection. So till now, we talked about the language features themselves, but jGuard is kind of tool also to detect misuses. So here we wanted to compare it against CogniCrypt, which is a misuse detector that consumes CrySL, right? And unfortunately, we had only CrySL specifications for cryptographic misuses. So what we did is we went to MoveBench and we looked at all the code that was using cryptography or Java cryptographic library. And then we tried to express these misuses using jGuard and also CogniCrypt. And well, the misuses detected were not that different, right? 25 to 26. But where jGuard obviously shines is that CogniCrypt reported like 67 false positives, whereas jGuard detected none. But this is kind of given because of the dynamic nature of jGuard, right? Of course, one thing natural to wonder is because jGuard injects code, what is the performance overhead, right? We could argue that, well, you should have had these checks in your API anyway, right? So it's not an overhead. But we did run some benchmarks. Part of them were synthetic examples, and part of them were real benchmarks, right? And in most cases, jGuard's performance was essentially the verified jar did not perform far worse than the native jar, right? But in some cases, as you can see, it's double the time taken. But we also explained why it is in the paper. Essentially, these were the synthetic benchmarks where we kind of created the worst case scenario, right? Where it runs like where it triggers the misuse like over an iteration of 10,000 or 20,000 or whatever, right? And finally, because we've implemented jGuard on top of MPS, we also have like cool tooling support for the API designers themselves. We have type checks. We have misuse detection, things like that, right? So yeah, that's the end of my talk, and I'm open for any questions.
Thank you. Any questions?
Thanks for the talk. So this kind of checking that your API object or your API is in the right state dynamically whenever you try to use it is something that API authors will usually do just anyway, or you could argue that this is a part of a good API is to do these checks dynamically. So does this tool, is the idea to make it easier to write these checks, or to have some sort of like discipline around writing them?
Yeah, so that's the argument, right? So because we've designed it based on these misuse categories, we kind of restrict you into. So essentially, the code is easier to are more readable to look at, right? These API checks that are more understandable. When you look at a jGuard code, or if you look at these checks that are encoded, first of all, it's not true that API designers put these checks because otherwise we won't have misuses, right? Otherwise we won't have research on misuses. So that doesn't happen actually. But even if it did happen, there is a benefit to jGuard annotated code because as someone who comes in and tries to make sense of the API itself, it would be much better than actually looking at the code, which is raw with these exceptions, right? So you can, the paper is there, and also jGuard is available online. You can check out these generated code. They're quite ugly to look at. So.
Got it. Thanks.
Any other questions?
Just a really simple question. Maybe I just missed it, but can you parameterize your guards by arguments? I presume often you want the state of the guard to be dependent on arguments that are being passed in, like a.
We have observed certain scenarios where this was needed, but currently we don't support it.
Okay.
But yeah, this would be something cool to have.
Yeah, thank you for the talk. With it, you didn't actually describe how this tool is used, but I envisaged it was sort of, it's a developer tool. I don't think you actually described like when this tool is used, but it's a developer tool that people use when they're building applications, or?
No, this would be the API designer's tool, right? So if you are implementing an API, you would use jGuard to encode these misuses as part of your implementation, and then ship. So you would use the jGuard compiler to get these verified jars, and then you would ship them. So if I'm a consumer of your API, I would just replace your I would just replace your older version without these checks with the version with the checks in it, right? And yeah.
Right, I understand. Because I kind of envisaged that you described how the misuses are getting detected over time, right? And new misuses are being discovered as, you know, cryptography libraries go out of date. I wondered about the sort of ability to have a tool like this where you retrofitted it later in the development process, i.e. once a library was released or once a application was deployed, even in a live system, I suppose, the rules got updated. Have you thought about that at all?
This would be this would be new versions, right? So as in, okay, your misuses have evolved, right? So for example, let's take the GC example. Yes, okay, AES was ECB was secure before. It's no longer secure now. With Zoom, actually, the scenario was that the key length was insecure, right? 128 bits was okay sometime before. It's not now. So you would just change these requirements on your library implementation, generate a new version, and ship it. So Once I get access to a view version, I should. And then, well, yes, there is the catch that it kind of depends on how good my tests are, right? So if I don't have a kind of test suite that covers all of my code, well, but this is true for all evaluation.
Thank you.
Let's thank the speaker again.